What's going on, guys? Agustin.AceTutoring here, AceTutoring. We're going to take a look at an Sn2 type question as well as the mechanism and the rate law for this process, and then we'll recap chirality. Hope you enjoy. Here you go. The question is, which of the following substrates will be the most reactive under these specified conditions? So if we're talking about E1, Sn1, E2, and Sn2, how do you know what to look for? How do you know what type of reaction it's going to be? The first thing that I would recommend you look for is the nature of the nucleophile, right? Because if you have a nucleophile with a minus charge, then that's going to tell you that is going to favor a type 2 reaction, Sn2 or E2, right? So how do you know, first of all, what's a nucleophile, right? It's any compound that has at least a lone pair. So if we were to compare, say, water versus sodium hydroxide, right? Both of these can potentially act as nucleophiles because we have lone pairs here, right? But you should know without designating formal charges, if you have a metal and a non-metal, that means that the metal will have a plus charge, and whatever this compound is, right, in this case hydroxide, will have the minus charge. So, point is, even if you've never seen sodium azide before, which is what this N3Na compound looks like, or what the name of the compound is, you should know that, okay, I've never seen this before, but I do know that this is going to have plus, which means this N3, the azide, will have the minus charge. So if you're making a little mental map, right, you want to cross out which reactions it could definitely not be, right? So we already identified this is going to be a what? Type 2 reaction. That means it's going to be Sn2 or E2. We crossed out Sn1 and E1. How do you know this is Sn2 or E2? Because things that are nucleophiles could potentially also act as bases, right? So if in this scenario this were to act as a base, we would call it a E2. If this is going to act as a nucleophile, we're going to call it a Sn2, right? Substitution nucleophilic. So, turns out that sodium azide, this N3 minus, is a stronger nucleophile than it is a base. So you know to cancel out this E2. There is something else that favors this reaction being Sn2, and that is the room temperature, right? It's definitely not a tiebreaker between E2 and Sn2. There are a few variables, but generally speaking, at lower temperatures, you're going to favor substitutions over eliminations. At high temperatures, when you have heat, then you know to do eliminations. But in any case, we've already identified that this is a Sn2 reaction. So what is an Sn2 reaction? Well, basically we have the nucleophile attacking the electrophile, aka the substrate, which is going to have the leaving group. So all of these four have leaving groups, but you should know that for Sn2, the nucleophile wants to attack the least hindered carbon, right? Kind of, it gives some personality to this. If this guy wants to attack the carbon, then it's going to be easier to attack the carbon that is most accessible, the least hindered, the most open for an attack. So hopefully by now you know that the leaving group for all of these is the bromine. So if we look at this, we know to cross out C based on steric hindrance. This is too hindered for a backside attack of the nucleophile. Remember, when we draw this on the board, it's stationary, but in reality, these molecules have free rotation, right? Because they're sp3 hybridized. So point is, you can kind of look at this group kind of like a bodyguard to this carbon, right? So it's very well protected. So that's not going to happen. So if we look back up here, right, this is a secondary alkyl halide, right, because this carbon with the leaving group has two carbon groups. This is a secondary alkyl halide. This is a primary, whoa, looks like a 10, primary alkyl halide. So if you think about it, this nucleophile has easier access at this primary alkyl halide, right? Because again, remember, keep in mind that there's free rotation. So this ethyl group here, I could, have drawn it this way. It's going to be under continual free rotation, and the point is, this carbon is more hindered than is this one. Hopefully that makes sense. But in any case, this is possible, right? And keep this in mind, anytime you see you identify that it's an Sn2 reaction, anytime you see a tertiary substrate, you should cross it out. And over here is one that it's kind of tricky, right? We're going to go back to this in a second, but for now, let's do both of these reactions, A and B. So if I were to proceed with this reaction, let's use a different colored marker here for the mechanism. So all organic chemistry reactions are nucleophile to electrophile. And those of you that I've tutored privately are probably laughing because I repeat that over and over again. That is one thing that all of organic chemistry reactions have in common: nucleophile to electrophile. Which is my nucleophile? Over here, right? Which is my electrophile? This guy, right? So why am I attacking this carbon in particular? Well, if you think about it, hopefully you should know about dipole moments and polarity. I have a negative pull that way, which makes that carbon partially positive. That's why this azide is more attracted to this carbon in particular. So you kind of want to get used to seeing things in your mind's eye, as I learned. You want to see things three-dimensionally. So anytime you see a wedge, it means that whatever group is wedged is coming out at you, right? So for Sn2 reactions, we're going to do a backside attack, which means this N3 is going to come in opposite to this bromine. So when we attack here, let me erase this so it doesn't get confusing. We attack here, we kick out the bromine, right? So as a result, because that azide came in the backside of this molecule, we can draw it this way. So one thing to keep in mind, all type 2 reactions are concerted mechanisms. That means it happens in one step. Please do not confuse that. A lot of students tend to, for whatever reason, they think that Sn2 means substitution nucleophilic and that it happens in 2 steps. It is not true. Sn2 stands for substitution nucleophilic bimolecular, meaning how fast this reaction occurs or how fast it happens is dependent on both the concentration of the electrophile and the nucleophile. So this would be the end result for the first question, right? How about over here? Well, this nucleophile again has to attack from the back, but in this case, I don't have a chiral center like I did over here. And this carbon is more accessible than is this one. So it makes sense that this reaction, B, will occur faster than A, right? Over here, it kind of has to get past this ethyl group and this methyl group. I mean, I guess I am trying to be redundant here, but I want to make sure that the point is clear. For substitution, Sn2, you want the least hindered alkyl halide or the carbon that has a leaving group, right? So the end result here is just substitute that bromine for this N3. And again, in this case, you don't worry about wedged or dashed because I don't have a chiral center. Now, one thing that's important to note is anytime that you have an Sn2 reaction, you're going to have a Walden inversion. And let's take a look at this molecule. Right? This is the primary alkyl halide. One problem though. It is primary, but we actually, this extension here will make this a neopentyl halide. Right? We'll write that down here. And this neopentyl refers to this group that is connected to the bromine. Right? So again, remember, all these carbons are under continual free rotation, and if you think about what that means, when this nucleophile goes to, excuse me, if you think about what that means, when this nucleophile tries to attack this carbon, it's not going to work out because it's going to be blocked by this neopentyl group. So the point is, there will be virtually no reaction. So again, anytime you see a tertiary substrate, right, a tertiary alkyl halide, or you can have leaving groups that aren't halides, right? So point is, anytime they have a leaving group attached to tertiary carbon, will not do Sn2. Anytime you have a leaving group attached to this neopentyl, you're likely to put no reaction on there. Let's end this segment with a discussion about the mechanism and the energy diagram for an Sn2 reaction regarding this particular molecule. So 2-bromobutane, right? So with 2-bromobutane, right, you should hopefully know by now that this is a chiral center, right? Again, chiral center, as far as organic chemistry is concerned, is an sp3 hybridized carbon that is attached to 4 different substituents, right? Completely different. In other words, you can say, oh, well, you have 2 carbons here, so this shouldn't be a chiral center. Well, not exactly, because these 2 carbons are different, right? Methyl group, ethyl group. So now we're going to designate chirality, RNS, based on the molecular weight of the direct atom that is connected to the chiral center. So this is my chiral center because I have 4 different substituents. And again, when you're doing chirality, you have to make sure that the hydrogen, well, not the hydrogen, the lowest group of the chiral center is going away from you. So now we're going to go designate this on molecular weight. Bromine weighs more than carbon, right? So 1 in between these 2, this will take priority. Because this is connected to another carbon, this has 3 hydrogens, right? So if you kind of follow this order of numbers, right, the way that they're arranged, we see that we're kind of making a right turn, right? Sometimes books tell you to go like this, but if you're taking a test and you're freaking out, you don't know if you're going right or left, or if you do this too long. So I like to just pretend, okay, I'm driving, which way am I going? Right, which makes this chiral center R. So the end result here, we have 1, 2, 3, right? So why isn't this R? Well, remember, as mentioned, anytime you designate chirality, you have to make sure that the lowest group of the 4 is going away from you. In this case, right, knowing tetrahedral geometry, if this N3 is dashed, that means that this hydrogen is wedged. So there's 2 things you can do here. You can kind of picture yourself going into the plane of the board, right? So now this molecule is directly in front of you. So I'm designating chirality this way. 1, 2, 3. So I would be making a left-handed turn if I'm going this way. That takes a little practice though, and if you're just starting with Argo, I just recommend just do this trick. If this is going R, but the lowest group is coming out at you, make sure you flip the configuration. So this actually is S. Get rid of all the stuff up here. Okay. So it makes sense that this took place because remember, with all Sn2 reactions, whether or not you have a chiral center, you're going to have a Walden inversion. So let's take a look at what happens. Again, remember, all type 2 reactions are concerted mechanisms, meaning they happen in 1 step. So what happens here is the nucleophile, let's erase this hydrogen, this neater, is going to attack the antibonding orbital of this carbon, right? And we kick out this bromine. So as a result, you have no intermediate because this happens in 1 step. If we were to look at an energy diagram here, energy, right, we'll start here and there, right? This is a favorable process and it happens in 1 step. So if we were to look at the transition state, which is also important to mention, right? This little bump here is the, in layman's terms, right? This is the energy of activation. So if we were to look at the transition state, which is also important to know whether you're taking MCAT, VAT, or just taking the Orgo class, you want to know that the transition state looks something like this. In other words, as we're going over this hill, what you have is, let's draw this garden. So if we were to look at a transition state for this following reaction, it will look something like this. Actually, it will look exactly like this. And again, notice that there's a difference between dashed and dotted lines. Hopefully you can see the difference there, but anytime you see dotted lines, it means that bonds are being broken or they're being formed. So this explains why this reaction is a concerted mechanism. With Sn1, or really all type 1, Sn1 and E1, it's a multi-step process because we have to first make the carbocation. But here it all kind of happens at once. So what we see here is, generally you'll see, oh, you can see too much. This is the nucleophile, and this will be the leaving group. And it makes sense that this is a type 2 reaction because how fast this reaction occurs, the rate of this reaction, is dependent on both the concentration of the nucleophile and the electrophile, aka the substrate. So if we were to look at a rate law for this particular reaction, it would look something like this. Rate equals K. Concentration of what's the nucleophile? A side. And then what is the electrophile or the substrate? R2-bromobutane, right? So hopefully you can see that. So that's what Sn2 stands for. Substitution, we had a substitution clearly, and it was a nucleophilic reaction, and it was bimolecular. That's what that 2 stands for. Please do not confuse that with Sn2 being 2 steps. That's not true. Sn2 is bimolecular. That's where the 2 comes from. I'm sorry to be redundant here, but I want to make sure that's clear. Okay, so that wraps up the short segment on Sn2. Hopefully you enjoyed it, you got something out of it, and thanks again for watching. There's going to be many more videos to come. Please contact me via email if you're interested in getting access to all my videos. I also do private tutoring and group tutoring. Be sure to check out the website, www.AceTutoringBoca.com. The link is provided below. So thanks again for watching, and I look forward to seeing you guys soon. Take care.